In this chapter, we study inertia tensor. The inertia tensor is defined for a rigid body system, which is a many-body system whose relative position of any 2 points is invariant. So it is assumed to be free of deformation. In a previous chapter, we studied the motion of two-body system governed by the central force. In that case, the kinetic energy is decomposed in terms of the orbital angular momentum contribution and the radial motion. The system of two-body system was described by the reduced mass, and the two components, tangential components that contribute to the orbital angular momentum, and the radial component of motion. In the case of a rigid body motion, that radial motion of any two particles inside in the system is not allowed. So only the rotational motion about a fixed axis of rotation is to be considered. Okay. In this chapter, we used this kind of terminologies. We use the total mass capital M for the mass of the system of particles, and capital XCM is the central mass of the system of particle, that rigid body. If we compute the inertia tensor, or with the inertia tensor we can compute the orbital angular momentum and the total kinetic energy, it involves the calculation of the inertia tensor. And inertia tensor may depend on the distribution of the particles. Suppose that we rotate a disk in an inertial reference frame. If it rotates, the distribution of mass depends on time. Therefore, the inertia tensor computed in the fixed coordinate system, the fixed inertial reference frame, the inertia tensor becomes the time-dependent one. So instead of using the inertia tensor in terms of the fixed inertial reference frame, we use the body coordinate system. That is the frame, that is the system whose axes are all attached, fixed to the inertial, fixed to the rigid body. In that case, the axis of reference frame acquires the time dependence, but that can be analyzed quite easily. Instead, the inertia tensor, because it is computed in the body coordinate system that is fixed to the rigid body, the inertia tensor becomes independent time. It is quite efficient to make use of the body coordinate system. So we use a subscript or superscript capital B to identify the frame of reference or variable is measured in the body coordinate system. So basis vector without any such a subscript or superscript capital B, that stands for the inertial reference frame S. If we write a vector, position vector of a particle, or velocity or acceleration of a particle inside the system of a rigid body, we use a vector notation, or sometimes this kind of form that stands for the matrix representation. So If it is a vector, we assume that x is a column vector. Just like that, the superscript b is attached to identify the position of an nth particle in a rigid body as a column vector, as a vector. And this is a unit vector of the body coordinate system. So this is an example of writing the components as a column vector. Okay. If it is written in a boldface form, then it is just a vector, normal usual vector notation. Okay. One important thing is in the body coordinate system, the position of each particle is fixed. Therefore, its a time derivative is vanishing, and its a double time derivative is also vanishing. So we remember how to express the position, velocity, and acceleration by making use of the rotating frame. In that case, for example, we compute the Coriolis force. In the rotating frame, a particle can move even. However, in the rigid body system, this coordinate of each particle in a rigid body described in the body coordinate system is fixed. So it is quite simple. There is a great simplification in the calculation. If we consider the rotation should be described with the angular velocity as a rate and the direction of the axis of rotation. We can write this omega in a vector form or the matrix representation as a column vector. This omega involves with the orbital angular momentum L or kinetic energy at T. When we measure the omega, it should be measured in the inertial reference frame. And in case if it is measured in the rotating frame, that can be simply measured from the rotating frame, just the negative value of the rotation of the space can be treated to be the omega. So whether we measure the omega in the inertial reference frame or a rotating frame in the body coordinate system, we say the body coordinate system, the two values are the same. That omega b and omega are assumed to be the same. Because of this, the position is invariant, and velocity and acceleration of an nth particle in the rigid body mass distribution is always vanishing. Only position is fixed. It's independent of time. But actually, if you measure those values in the inertial reference frame, we know that the basis vector of the body coordinate system is changing depending on time. This is the general descriptive form of the motion of a rigid body described in terms of the inertial reference frame variable. At an inertial reference frame, the center of mass of this rigid body is placed at xcm. At time t1, it is placed like that. But after some time, after time goes on, the position of center of mass can change like that, and even the axis of body coordinate system can change. But as far as we describe the rigid body motion in the body coordinate system, the x and body is always the same. But the change of those unit vectors of the body coordinate system can be simply described by the Rodriguez formula for finite rotation. We recall that the Rodriguez formula for finite rotation can be employed to find out the velocity and acceleration of the particle. The left-hand side is described in terms of the inertial reference frame variable, and these the xcm is the position of the center of mass of the rigid body. And as far as the first time derivative is concerned, the rigid body's central velocity plus each particle has the additional velocity relative to the center of mass of the rigid body. That is omega across the level arm. That the position vector from the center of mass. We assume that the axis of rotation is passing through the center of mass. If we compute the acceleration, this omega may vary, so time derivative of angular velocity will give the angular acceleration across the level arm. In addition, because the frame of reference is rotating with omega, we have another cross product of omega cross to this vector to find out the centripetal force. By making use of this notation for the velocity of the nth particle in a rigid body, we can compute the total kinetic energy of a particle by squaring this and multiplied by the mass of that particle summed over the indices small n runs from 1 to capital N, if the capital N is the number of particles consisting of the rigid body. After calculation, we will find that the total kinetic energy of a rigid body is a sum of two components. First one is the translational kinetic energy, and the second one is the rotational kinetic energy. Unlike the case of arbitrary motion of a system of particles, the motion of a rigid body is quite simple, that does not have any radial motion. I mean, the rotation about the axis of rotation will lead to the tangential motion that makes the orbital angular momentum. So it is quite very simple in comparison with the case of two-body motion in for a celestial body. The translational kinetic energy is the kinetic energy of a single particle of capital mass m that is the same as the total mass of the rigid body multiplied by the velocity of the center of mass. Thus, the total kinetic energy becomes a translational kinetic energy if the size of the rigid body is 0. So if it is just a point, the total kinetic energy is just the kinetic energy of a single particle. However, the rigid body rotates about the axis of rotation omega. Therefore, there should be a rotating motion that is always tangent to the radius. The level arm can be obtained by omega cross x. The magnitude of the omega cross x bn is the distance from the particle to the axis of rotation. multiplied by the rate of rotation, so angular velocity. So, in summary, total kinetic energy of the rigid body is a sum of translational kinetic energy and rotational kinetic energy. If we consider the motion in a general inertial reference frame, what we have to do is just compute the total kinetic energy. And this velocity of an nth particle is the sum of central mass velocity plus omega cross the level arm. And if we substitute in here, we find that there are only two non-vanishing contributions. First one is the translational kinetic energy, and second one is the rotational kinetic energy. You can follow this calculation, but basic idea is summarized in here. Square of the sum of two vectors is square A, square B, plus 2 times the scalar product. Substitute the velocity of the center of mass and velocity, tangential velocity due to the rotation of the nth particle of the rigid body. We consider A dot B. A dot B is just the scalar product between these two. We find that it is just a triple scalar product, and triple scalar product can also be written in this form: cross product times some scalar product. And this is common to every particle n, for n goes from 1 to capital N. We notice there is a summation over n, after multiplying mn, the particle n's mass. And summation will give this factor becomes the total mass times the center mass. But as we know, the body coordinate system has the origin at the center of mass. Therefore, the XCM body coordinate system is just exactly the zero. Therefore, the cross term in this expansion vanishes completely, and only two contributions. And each contribution has the translational kinetic energy, this one, and the second one has the rotational kinetic energy. This rotational kinetic energy can be written in a simple form in terms of the in terms of the inertia, moment of inertia. No, inertia tensor. Moment of inertia is a single value, and the inertia tensor is ranked to Cartesian tensor. The computation of translational kinetic energy involves this calculation. And if we apply this identity, we can express this in terms of this. That expansion can be simply made by considering the Pythagorean theorem. 1 plus sine squared cosine squared sum is just the cross product of a and b squared divided by a squared b squared. And this one is a scalar product of a and b squared divided by a squared b squared. Reorganizing this identity, we find the cross product squared is a squared b squared minus a dot b squared. This formula can also be derived in terms of by making use of the backhand rule. Just copy this result, and we just replace x cross b behind with the capital C, and this one becomes the triple scalar product. And we reorder this triple scalar product, and we face the a dot equals to C. Again, we substitute C, return to a cross B. Now this is a triple scalar product that can be computed by making use of the back-cap rule. A is B, B is A, and C is B. So B, this A is factored out, back, A, C. So B dot B appears here. Cap minus cap C. C is B, A dot B. All right. So computing the scalar product, we find this A squared B squared minus A dot B squared. All right. And the angular velocity can be written in a matrix form or just a vector form. Linear, it's a linear combination of basis vectors. All right. Thus, the translational kinetic energy, rotational kinetic energy can be written in this form. We have omega squared xnb squared minus omega dot xnb squared sum over n multiplied by each mass. Now this omega squared is omega I. That is, we can rewrite this one as omega I omega j delta ij. That is omega squared, and x and b squared is copied in here. We have omega dot x, so repeat once and twice. So in these two terms, we have common vectors omega I and omega j. Let us pull out this factor out, omega I, omega j. Then summation is here, and remaining piece will be delta I j x and b squared and x and I x and j b. So this is a 1/2 omega I multiplied by iij. This is the definition of iij and omega j. So kinetic energy can be written in a matrix form, 1/2 omega transpose I omega. All right, here I is called the inertia tensor. Inertia tensor. Inertia tensor has the form canonical delta and xi, xj. And here's our squared style. If we compute the inertia tensor for a continuous mass distribution, the summation over n is to be replaced with the integral over the space of the mass. And this differential of mass can be written as a form product of a density function, mass density distribution, multiplied by the differential of the space. All right, because these xb's are constant of time in the body coordinate system, this one can be used for independent time. However, if we compute the inertia tensor in the inertial reference frame, because the rigid bodies keep moving and keep rotating, we should compute a very complicated form. This is the main reason why we introduced the body coordinate system to compute the inertia tensor in the simplest form. We notice that the inertia tensor has a symmetric under exchange of I and j, and because position and canonical delta have mass, everything is real, therefore real and symmetric matrix. We know this real and symmetric matrix is a Hermitian matrix. If it is a Hermitian, then the matrix can be diagonalizable, and the eigenvalues of that matrix must be real, and there should be 3 eigenvalues with multiplicities. Sometimes 3 of them can be the same, then it is called the triply degenerate, and 2 values are the same, it is doubly degenerate. If 3 eigenvalues are all different, then we can say non-degenerate case. All right, for each eigenvalue, we have eigenvector, and every eigenvector must be orthogonal to the remaining eigenvector. There is a straightforward way to find out the normalized eigenvector. Once you normalize the eigenvector, we can, because that forms a complete set of the Hilbert space, we can always make use of the completeness relation by a direct product of eigenvector and its a Hermitian conjugate summed over all eigenstates. Once we finalize to compute the inertia tensor, we should find that the orbital angular momentum, ith component of the orbital angular momentum, can be computed as this multiplication of inertia tensor and the column vector for the angular velocity. The kinetic energy of a particle and of a rigid body can be computed by computing this 1/2 omega iij, omega j. The explicit computation of matrix elements for the inertia tensor can be done in the following way. We have a tensor structure delta ij x squared minus xi xj multiplied by the density, mass density of mass distribution integrated over the space. Each components are given in here, and this is how to obtain those components. x11 has the vector delta 11 x squared minus x1 squared. Delta 11 is 1, and x squared is x1 squared, x2 squared, and x3 squared. If we subtract this one with the minus x1 squared, we have x2 squared plus x squared, x3 squared. That means it is perpendicular to the x-axis. Perpendicular distance squared from the x-axis. In a similar manner, I22 has a vector of perpendicular distance from the y-axis, and I33, all three diagonal components, represents the row times perpendicular distance from that axis. Okay, so only x3 is missing in this term, and x2 is missing in this term, and x1 is missing in this term. What about the off-diagonal contribution? 1-2 case, Kronecker delta vanishes for any I and j with the different indices. Therefore, the off-diagonal components is always a minus product of the two components, 1, 2, x1, x2. 1, 3, x1, x3. 2, 3, x2, x3. It is manifest that all of the contributions are symmetric. By definition, it is a symmetric matrix, so we do not have to compute everything. We can make use of the symmetry of the system to find the complete expressions as quickly as possible. It is rank to Cartesian tensor. Therefore, we can make use of the rotational property for the vector. A rank to Cartesian tensor is transformed under rotation like that. Let us check it explicitly. Suppose that we have inertia tensor delta ij defined in a coordinate system. We remember that delta ij is the rotationally invariant rank to Cartesian tensor, and x squared is invariant under rotation, and we have xi and xj. xi and xj has the property of rotation. If we substitute xi prime, then xi prime is rij multiplied by xj prime. In a similar manner, the product xi xj transformed into xi prime and xj prime like that. This is the result. All right. If we transform this into the rotated coordinate system, we have scalar function. We remember the scalar function is independent of rotation. This one should be the same. And we have a coordinate rotation. The Jacobian appears. But Jacobian of this rotational transformation, Jacobian becomes determinant of R. If we make use of a proper rotation that does not involve inversion, then determinant of the rotation matrix R is just the identity. It is just 1. And x prime square, this is scalar product. This is invariant on the rotation. Only this guy rotates like RIA, XA, RJB, XB. All right. Therefore, we made use of the fact delta ij transformed into itself and R is orthogonal. Combining these two relations, we can rewrite in this form. That means this is the original inertia tensor, AB component, and this one in here, this one can be rewritten in terms of the transpose matrix. Then the final result will be like that. For every component I and j, we find this relation. That means the rank to Cartesian as the rank to Cartesian tensor, inertia tensor transforms like that. So let us consider a very simple case. Single mass. It is fixed on the x-axis. Mass m is fixed on the x-axis at this point. If we substitute, so this is a single particle. Therefore, we raise the summation notation, and each particle, just a single particle of mass m, and these components, we substitute x1, x2, x2, x3 with the a, 0, and 0. So, here, x2, x3 is at 0, 0, 0, x2, x3, 0, 0, 0, 0, 0, 0, 0. So red one are all zeros, and remaining piece this one is just a 0, 0, 0, symmetric, 0, 0, and 2, 3, 0, symmetric. This is 0. These two survive, and x2 is also 0. Only x1 survives. x1 is a, so we have a squared, a squared. The answer is ma squared, this multiplied by this matrix. If it is the case, angular momentum is inertia tensor times column matrix omega. And if we have omega 1, omega 2, and omega 3, we'll find that ma squared, 0, omega 1, omega 2, omega 3. So this one, if omega 1 is a non-zero, orbital angular momentum is not parallel to omega. Orbital angular momentum is parallel to 0, omega 2, omega 3. However, omega, angular velocity, is parallel to omega 1, omega 2, omega 3. These two vectors are not parallel as long as omega 1 is non-zero. Instead, if we choose 0 omega 0 or 0 0 omega, then the orbital angular momentum is still parallel to the axis of rotation. We call the axis of rotation that follows parallel. This orbital angular momentum is parallel to the omega. If we choose omega 0 0 or 0 omega 0 or 0 0 omega, then we can always find the orbital angular momentum to be the same as the parallel to omega. But this is only true. This is only true when the matrix is diagonalized. Sure, because it is a real and symmetric, we can always diagonalize. But before it is not diagonalized, this relation is not true. The finding out the principal axis in a general coordinate system is therefore quite important. As long as we have found the principal axis, then the total kinetic energy can be written in a simple form. The principal value for the inertia tensor multiplied by just omega squared itself. The principal axis means 1 0 0 0 1 0 0 0 1 as long as the inertia tensor is diagonalized in such a way. In that case, the total kinetic energy will be like that when we rotate about the axis, like that when we rotate about the y-axis, like that when we rotate about the z-axis. This is true only when diagonalization is achieved. Next, we compute the inertia tensor for a distribution of particles. The first example is the finite uniform rod of length L, whose center of mass is at the origin, and it is along the x-axis. In this calculation, the mass distribution can be expressed in terms of theta and Dirac delta function. As you know, the value of y and z are all 0 except at these points. So it is very good to use the delta function. This one vanishes whenever y is non-zero. So we make use of the property. This Dirac delta function integration is always identity, but Dirac delta function is 0 except at y equals 0. The same is true for the z distribution. So we have a product of delta y and delta z. And we have a finite region between 1/2 L and minus L. So we have Heaviside step function, theta function. Theta function is a 1 when it is positive. Theta function is a 0 when the argument is negative. I don't care about the point at t equals 0 because the theta function is useful only for integration, that the contribution at t equals 0 does not, the contribution is vanishing. So the product of these two theta functions, the first one is 1 survives only for x is less than 1/2 L. The second contribution, this vector, survives only when x is greater than minus 1/2 L. Alright, so we can substitute, we can make use of these conditions we have over vector m over L, then we finally obtain the mass distribution. In order to check this it is true, we can integrate over the space, and the final trivial result shows that it is m. Remember, density function has a dimension of mass divided by volume, but here we have only length dimension. The reason is that each delta function is a function to be integrated over the length. But after the integral over y and z, it becomes 1. That means dimensionless. The length dy has a dimension of length. Therefore, the delta function of y has the dimension of L minus 1. This one too. Therefore, this double delta function gives the dimension of length squared in the denominator. Therefore, we have the correct physical dimensions of this density function. Let's see. We have Dirac delta function for y and z, that means delta x2 and delta x3. In the calculation of the inertia tensor, we have x2, x3, x2, x3 are all vanishing. Therefore, if we make use of the fact that vanishing x2 and x3, most of the contribution except for these two contributions disappears. So these two integrals are identical to each other. So it is proportional to 1, 1. And what is the value for that moment of inertia? This integral involves minus 1/2 L to 1/2 L dx1 x1 squared. This is a even function over minus something to plus something, and these are the same in magnitude, so it is double of the integral from 0 to something. The answer is this. So L cubed over 12. The factor of m over L appears in the density function. Therefore, 1/12 of ml squared will be the eigenvalues for this matrix. That means we have a rod along the x-axis First of all, this is a principal axis. So if the principal axis is E1hat, that means 1, 0, 0, eigenvalue I1 equals 0. So moment of inertia along this direction should be vanishing. Moment of inertia about this y-axis, that is 1/12 ml squared. Moment of inertia along the z-axis, because of symmetry, this moment of inertia about the z-axis and y-axis must be the same. They are both 1/12 of ml squared. And so E2, E3, these three are principal axes of this, and both of them has value I2, that is 1/12 ml squared. So our I, diagonal form, it is already diagonal form, I1, I2, I3, 0, 0, 0, 0. Next, we consider a disk. The mass distribution of this disk on the xy plane can be written in this form. Mass divided by area, and there's a theta function that the planar radius is less than r, and there's a delta function to restrict this plate on the plane at z equals 0. Let's check if this distribution has the correct value. We notice that the density integrated over space must be the same as total mass. Copy the factor m over pi r squared. Now it is better to use the cylindrical coordinate system. Rho theta runs from 0 to 2 pi, and this is scale factor for the angle theta. Sure, the cylindrical coordinate system, we usually write phi instead of theta. We have scale factor and z integral. Now the theta function is replaced with the planar radius integral 0 to r. Alright, the integral over z is trivial. This delta function gives 1. And the radial integral is rho d rho, this is 1/2 r squared. And azimuthal angle rotation, this integral is just simply 2 pi. Factor 2 to cancel, r squared cancel, pi cancel. So we end up with the mass, total mass of the rigid body. That is correct. So let us keep using this mass density distribution. We recall that the rho, the density function, has the factor of a Dirac delta function, delta x3. So we had better remove all the factors, all the terms that contains the factor of x3. So x3 appears here and there. If we remove everything, non-vanishing contributions will be x2 minus x1 x2 minus x1 x2 x1 squared, something like that. The calculation will be very simple. Let's do the calculation for I12 first. We make use of the previous parameterization for the density function m over pi r squared and rho theta and delta function integral for z integral is trivial. Now x and y are expressed in terms of rho cosine and rho sine. We substitute these results in here. But we find that the integral, this integral, angle integral involves odd function integral from -1 to 1. So it vanishes. Or we can rewrite this one as a 1/2 sine 2 theta. A sinusoidal function integrate over a period or n times a period, it must vanish. Therefore, because of that symmetry, that contribution is actually vanishing. So what we have to compute is just the diagonal component. And in addition, we find this integral and this integral, they are the same. Because x1, x2 are symmetric on the exchange because this disk doesn't change its own shape under the rotation about the z-axis. Therefore, this value and this value should be the same. In addition, the sum of these two will be the same as this. That is called the perpendicular axis theorem. So let us compute I33. I33 has the radius, the planar radius squared. Therefore, the calculation involves a z integral is just 1. Rho square will be combined in here to have a rho integral, the 1/4 r to the 4th power. And the azimuthal angle is integrated over the 2 pi. The final result will be 1/2 mr squared. As I already stated, just these two components will be just 1/2 of this amount. Therefore, the z component will be 1/2 mr squared, and x and y diagonal component is 1/4 mr squared. So let us consider the relationship between the inertia tensor and orbital angular momentum. Orbital angular momentum can be of a system of particles can be computed by the position cross the linear momentum summed over the all parts of all particles consisting of the rigid body. After calculation, we shall find that the total angular momentum of the system is a sum of this and this. And left one is actually the orbital angular momentum of a single particle of mass capital M, which is the total mass of the rigid body, concentrated at a single point. The second contribution is the angular momentum due to the rotation about the center of mass of a rigid body. We shall find that contribution, that relative motion about the center of mass involves the inertia tensor Iij. The position of a particle in a rigid body can be computed by summing the center of mass position and the relative position from the center of mass. And we again make use of the body coordinate system to describe a particle inside a rigid body. The linear momentum of a particle can be computed by taking the time derivative of these two. As we know, the time derivative of x and b itself is vanishing. However, xb is a rotating frame. Sb is a rotating frame. The velocity of the particle measured at the inertial reference frame should be computed as omega cross the lever arm. So if we substitute to this original formula for the orbital angular momentum of each particle, we have that. This one involves expansion of this cross product involves the 4 contributions, and only the 2 contributions survives, and the contribution that has a single power of xn must vanish, because that contribution has always mass times rigid body point measured in reference to, relative to the central mass. This one is a capture, this one, and this one. These two, sum over n and n, x and b, this vector, it is just mass times this guy. Mass times cm. And body coordinate system, this is exactly the 0. Therefore, these contribution vanishes. The only, oh no, not this. xn appears once again. x1 appears only once. This one, and this one. These two contributions vanishes, but we have this xb twice. That one does not vanish. The first contribution is if we sum over n, we have a total linear momentum. So center mass position cross total linear momentum. So orbital angular momentum of a single particle, single point-light particle whose mass is the same as the total mass m of the rigid body. If the size of rigid body is 0, then the total angular momentum is this one only. However, if it is a sizable, the contribution of relative momentum, rotating contribution about the axis of rotation passing through the central mass will contribute. That is to be measured in the body coordinate system. The orbital angular momentum relative to the central mass of the rigid body can be computed in this way, and we remember this one can be written in the form omega I b squared. We can pull out omega j to the right side. This is one this is omega j, but this is omega I. Therefore, we need to replace omega I with delta ij multiplied omega j. That's fine. What is that? This is the inertia tensor. Therefore, the orbital angular momentum of the system relative to the central mass is the product of inertia tensor multiplied by the angular velocity. In addition, the rotational kinetic energy can be written in the form. We recall that the rotational kinetic energy was 1/2 omega I, iij, omega j. If I make use of this, it is 1/2 omega I, Li. This one is Li, right? So this one can be written in the form, in a matrix form, omega transpose L. That means whenever omega 1, omega 2, omega 3, L1, L2, L3. Or this one can be written L1, L2, L3, omega 1, omega 2, omega 3. Right? That is 1/2 L transpose omega. Or 1/2 omega transpose I omega. In any case, everything will be the same. Now let us consider the Huygens-Steiner parallel access theorem. parallel axis theorem. First, we have computed the inertial tensor in the body coordinate system, whose origin at the center of mass of the rigid body. What happens to the case if we introduce another coordinate system whose x, y, z axes, these two, and these two. All three axes are parallel. The only difference of the two coordinate systems is the shift of the origin. So I is computed on the SB, whose origin is the center of mass, but in a frame as a parallel, the center of mass coordinate is A. Center of mass of the rigid body is A, except that all three axes, x, y, z axis and x, y, z axis for the parallel system as parallel will be parallel. The result is that involves this one, and this as parallel is just sum of A plus the coordinate measured from the body coordinate system. So addition of this finite value for the finite shift vector, we expand in powers of A, no A, single A, and double A. Double A. Single A has a contribution of this or this. Everything will be vanishing because this is the center of mass in the body coordinate system. Center of mass of body coordinate system is the origin. So these two vanishes, and this is the original value in the inertial tensor measured in the body coordinate system, and this is the additional piece coming from the shift of the coordinate. And the shape is, structure is exactly the same, except that we do not have to sum over all particles. This summation of particles just capital M, and we do not have to have weighted average. This variation depending on the particle appears only in the original definition, and A is independent of each particle, so this is a constant tensor. Alright, so Stylus parallel axis theorem can be applied to have this additional value added to the original value in the body coordinate system. So let us make some application. In a previous case, we considered the disk on the xy axis, and it was found to be diagonalized. So principal axis, x, y, z axis. Let us compute the inertial tensor after shifting the center of mass from here to radius A with an angle of 45 degrees with respect to x and y axis. Because A is given here, we make use of this A, substitute this result to find out the change of the inertial tensor. We can make use of the expression to find out the shift of the matrix. And this one can be added to the original contribution to the inertial tensor to find out the resultant tensor, inertial tensor, about those parallel axes. Alright, we recall that the inertial tensor is real and symmetric. if we have the principal axis, then the orbital angular momentum is parallel to the axis of rotation. To find out the parallel axis, it is convenient to diagonalize the matrix. And diagonalization of a real symmetric matrix is trivial because, first of all, the inertia tensor is real and symmetric. Therefore, it is a Hermitian matrix. Any Hermitian matrix is diagonalizable, like that. And these diagonal elements in the diagonalized matrix is real. And for each eigenvalue, there is an eigenvector. In this space, those eigenvectors are elementary unit vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. In general, matrix is not diagonalized yet. So, to find out this representation, we need to construct a rotation matrix that transforms this matrix that has the off-diagonal contribution to this kind of state. As we already studied in the matrix chapter, diagonalization of the matrix chapter, the elements, all of the row elements of this transformation matrix lambda is composed of the Hermitian conjugate of the eigenvectors. And these eigenvectors can be found by solving the eigenvalue equation of that inertia tensor. And here, the eigenvalue II, capital II, represent the principal value for the eigenvalues. We recall that the eigenvectors are orthogonal. We can always find the normalization for once you find out the eigenvector, then you have this one. Where I is not summed over. So this one is normalized eigenvector. Once you find out the normalized eigenvector, they satisfy the orthonormal relation. Once they satisfy the orthonormal relation, then the inverse of this matrix is just Hermitian conjugate, that is psi 1, psi 2, and psi 3 as a column vectors. So lambda becomes unitary. So inverse matrix can be obtained in a trivial way. Because the inertia tensor is a matrix composed of whose elements are all real, this Hermitian conjugate can be expressed in terms of the transpose. Alright. The principal axis can be found by transforming this in the original coordinate system. Principal axes are just psi 1, psi 2, and psi 3. And after diagonalization, after multiplying this transformation matrix that diagonalized the inertia tensor to these eigenvalues vectors, the resultant eigenvector is just a trivial one, 1, 0, 0, 0, 1, 0, and 0, 0, 1. In this space, the inertia tensor becomes diagonalized. We can apply the diagonalization method to diagonalize the case that appears in the 14. And we go ahead with the finding the eigenvalues and eigenvectors. If we pull out the over factor 1/4 of mr squared, we have eigenvalue equation is simplified into this form. The eigenvalues for these three values are all different, and they are called the principal values for this inertia tensor. For each principal values for inertia tensor, we have eigenvectors, and those eigenvectors are found to be this, and this. All three eigenvectors are orthogonal, and if we choose the unit normalization, you will find that the completeness relation psi I, direct product of psi I dagger, summed over I, that is identity matrix. This is completeness relation. And if first you need to find the scalar product. Psi 1 can be, for example, if we made a vector notation, this is square root 2 1 plus E2, psi 2 vector, square root 2 minus E1 plus E2, and psi 3 vector is just E3 hat. We can always construct the triple scalar product of unit vector to be 1, then it becomes cyclic. In that case, determinant of lambda should be plus 1. Okay? You remember the lambda is psi 1 dagger, psi 2 dagger, psi 3 dagger, and the lambda dagger is a psi 1, psi 2, psi 3, right? So determinant of lambda, this one is, because of this is 1. And once it is 1, it becomes, because lambda dagger is lambda inverse, it is unitary. So this one is the same as this, and in this inverse is this, so determinant of lambda is also identity. So in summary, we bring these three values for the eigenvectors. Hermitian conjugate of this eigenvector is 1 over square root 2, this. Hermitian conjugate of this will be minus 1, 1, 0, square root 1 over square root 2. Hermitian conjugate this will be 0, 0, 1, and we have the over factor square root 1 over square root 2 to find this one. And lambda inverse will be the lambda dagger will be obtained by flipping the row and column indices and then taking the complex conjugate, because they are real, it is just equal to the transpose of that matrix. If we make use of this transformation matrix and original inertia tensor, the resultant inertia tensor after rotation will be diagonalized, and these are These are called the principal values of the inertial tensor I. Okay. So now we have completed the basic fundamental studies of the inertial tensor, and in the next class we apply these old methods to consider explicit calculation of the inertial tensor for more complicated objects.